Hello all. So this class is based on sequential circuit, which is very important topic if we talk about digital electronics, right? This is core and mostly the question asked in interviews or gate or many examination are based on this topic only because it is little tricky, little complex than other than because students feel like this is a different domain and other topics before sequential circuit like combination, logic gates, number system and everything are different subject. This is important as well as easy to learn if we learn it, right? If we talk about sequential circuit, the basic building block of a sequential circuit is known as a flip-flop. Flip-flop. In flip-flop, we learn about many flip-flop, basically four in common. If we say SR flip-flop, JK flip-flop, T flip-flop, and T flip-flop. In these flip-flop, we learn about their truth tables, their excitation tables, and many other things. Basically, flip-flops are nothing. They are one bit storing elements. They store bit, one bit in them, right? And when we combine these flip-flops together, we talk about sequential circuit. In these sequential circuit, we mainly talk about registers, counters, registers. Registers are four types: serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. There are four types of register we talk about. We talk about counters. Counters are mainly synchronous and asynchronous type of counter we study. All the theory you can learn in theory classes. Now we will move on to the questions which are very important to understand, right? Moving on to the next question. Sorry, moving on to the first question. Okay, so first question says that in the given sequential circuit, so the sequential circuit is given, so two flip-flops are given. One is D and other is also D, right? Okay, so two flip-flops are given, D and D1 and D2. And they are saying that in the given sequential circuit, initial states are Q1 is equals to 1, Q2 is equals to 0. For the given clock frequency 1 megahertz, the frequency of a signal Q2 in kilohertz will be. So if we talk about a flip-flop, if we talk about a sequential circuit, we talk about three things, right? Output, basically the output of the flip-flop, we consider it as their next state. What will be the output and what is their next state? Other thing we talk about is the previous state and their type of flip-flop. Like this is D and D. If we talk, if we draw the excitation table of D flip-flop. D flip-flop, when it is 0, so output will be also 0. When it is 1, the output will also be 1. And output here is nothing but their next state. So that will be their output. So this is the excitation table for D flip-flop. Now they are saying that the previous state, so the previous state, for example, this value here, they have fixed it like 1 and 0, 1 for this flip-flop and 0 for this flip-flop. Now they are saying that the clock frequency, the clock is applied to both the flip-flops. If clock is applied, same clock is applied to both the flip-flops, that kind of sequential circuit is called synchronous, because they are in sync. They will work in sync. At same clock, both the output will be changed, right? Now so this was the excitation table for D flip-flop we saw here. Like just draw the table. In this, if we talk about sequential circuit, mainly we draw a lot of tables. From the tables only we understand that what will be the output and what will be the result, right? So now in this table, from the clock we will start. Okay, clock. So we'll talk about clock. Now, first input D1, which is nothing but it is connected to Q2. I can write it here, right? Next one is D2. D2 is connected to Q1 bar. And of course, we'll talk about the outputs, and the outputs are Q1 and Q2. Here Q1 is the output and Q1 bar is the complement of that output. Similarly, Q2 is the output of D flip-flop and Q2 bar is the complement of that particular output, right? And where Q2, let's just write in this term only, Q1 and Q2. This is Q1 and this is Q2. Now they are saying that initial values are 1 and 0. So for Q1 is 1 and for Q2 it's 0. These are the initial value. That means I can say that at clock 0, the initial values, this we don't know initially what were the inputs, but the outputs I know. The outputs were 1 and 0 initially. When the first clock pulse come, right, when clock is like moving like this is active high. So whenever the clock is high, the output will change. So when the first clock pulse will come, whatever values of D1 and D2 are there is set because of the values of Q2 and Q1 bar, because they are dependent on that. So D1 is equals to Q2. So Q2 value, this is Q2. So Q2 value is 0 and D2 is Q1 bar. So Q1 bar will be equal to 0. And the output, according to the excitation table of D, when D value is 0, output is also 0. So it is 0, 0 again. Next clock pulse. What happens to the next clock pulse? When next clock pulse, the value here, input value depend on the output, the previous outputs, right? So D1 value is equals to Q2. So Q2 is this. D2 value is Q1 complement. So Q1 was 0. So its complement will become 1, right? And the output will be same, right? D table is very easy. When the input is equals to 0, output is also equals to 0. And when the input is equals to 1, the output is also equals to 1. It's that easy, right? When the third clock pulse come, right, D1 is equals to Q2. So it is equals to 1 and D2 is equals to Q1 bar. So Q1 is 0 and its bar will be 1. Output will be same. Fourth clock pulse. We have to repeat these clock pulse until the output repeats its cycle again, right? The complete cycle of output repeats itself again. So we have to count up to that, right? So D1 is equals to Q2. So Q2 is equals to 1. D2 is equals to Q1 bar. So Q1 bar is equals to 0. Now output is equals to 1 and 0 again. Now you can see that it's again 1 and 0. It started from 1 and 0, right? It started from 1 and 0 and it's 1 and 0. If I move like this, I will get same result again and again. So at this particular point, the cycle stops. I can say that after 4 clock pulses, after 4 clock, output repeat itself, right? The same values repeat itself. So what it's saying that what is the frequency of Q2 in kilohertz? So it is repeating itself after 4 clock. So main clock was 1. So frequency F0 will be equal to 1 megahertz divided by 4. So that will be equal to nothing but 250 kilohertz. Easy? Easy? The main clock is 1 megahertz and the output is repeating itself after after four outputs, right? Four clock, after four clock, 1, 2, 3, 4, it will repeat itself, right? So the output frequency will be 1 megahertz divided by 4, which will be equal to 250 kilohertz. Easy? Moving to the next question. Right. Next question says that the synchronous sequential circuit, so now they have easily said that there is the circuit, given circuit is synchronous. Why? Because same clock is given to all the three flip-flops, right? So synchronous sequential circuit shown below works at a clock frequency which is given as 1 gigahertz. The throughput in m bits per second and the latency in nanoseconds respectively are. So what is throughput and what is latency, we will see here. Now what is this kind of, this is a register, right? This is taking some input and giving the output serially. So it is serial in and output is also given serially out. Serial out. So depending on the register, whether it is a serial in, serial out, serial in, parallel out, and other two things, parallel in, parallel out, or parallel in, serial out. So latency and throughput changes, right? If we talk about this particular type, serial in, serial out, we first find out the time. So time is equals to 1 by 1 gigahertz will be equal to 1 nanoseconds. Here we can see 1, 2, 3 flip-flops. So latency in serial out is equals to n t clock. So this is t clock, given here is frequency of clock, right? Here n is number of flip-flops. The number of flip-flops is 3. T clock we just calculated is 1 nanosecond. So what is the latency? 3 nanosecond will become the latency of the given type of register circuit, sequential circuit. Now they are talking about throughput. Throughput is number of bits per second. Number of bits transmitted per second. So according to the clock, we can see that here 1 bit is taking how much amount of time? 10 raised to power minus 9 10 raised to power minus 9 seconds, or you can say 1 nanosecond. Or you can say 1 nanosecond, because clock time is 1 nanosecond. So after one clock is passed, 1 bit is being transmitted. So 1 bit is taking 10 raised to power 9 minus 9 seconds. So how many bits throughput will be? Throughput will be 1 by 10 raised to power minus 9 will be equal to 10 raised to power 9 bits will be transmitted in 1 second. So that will be your throughput. 10 raised to power 9 bits will be transmitted in 1 second. So this is how we calculate the throughput. So throughput is number of bits per second and latency is depending on type of register we are talking about, right? Right. Moving on to the next question. Okay, so this question is on state diagrams. So question says that a state transition diagram with states A, B and C and transition probability from P1 to P7 is shown in the figure, right? That means, what does P1 means? P1 denotes that probability of transition from state A to B. That here P1 is the probability that state A will change to state B, right? So they are asking that for this state diagram, which of the following statement will be true, right? So how to solve these state diagrams? Now what is happening? So there are like three states, right? Three states we have to check about. Our one state is moving to another, right? P1 is the probability of changing A to B. From, if we are changing A to B, the probability is equals to P1. If A is stays at A only, the probability is P7. If A moves to C, the probability is P4. Now here we can see all the output probabilities from state A changing to any other states are in total 3. P1, P7 and P4, right? So basically they are saying that from state A, either it can move to B or C, or it can stays at state A itself, right? So these are the three cases, maximum 3 cases they are possible. So if I have to say that all the 3 probabilities from moving from state A to any other state will be equal to 1. So P1 plus P4 plus P7 will be equal to 1, because 1 is the maximum probability. All the cases we have taken, if we take all the cases, the probability becomes 1. Similarly, we can talk about other 2 states. So let's just talk about state B. So from B to B itself, the probability is P2. And from B, now B is moving to A. B is not moving to C, right? B is moving to A, the probability is P3, right? This also we can say that P2 plus P3 will be equal to 1. Now let's just talk about state 3. So from state C, the moving probability from C to C is equals to P5. And C is moving to A only. It's not going back to B. To A, it is equals to P6. So we can say that P5 plus P6 is also equals to 1. So these 3 conclusions we can calculate from our given state diagram. Easy, there is no rocket science in it. Just take one state at a time and find all the outgoing probabilities, right? So for A there were 3, for B there were 2, for C there were 2, right? We just calculated them and the sum of all the possible probabilities will be equal to 1. Now we have to match the option. So this is a multiple select option, right? Select the statements. So these are multiple select option. So now let's just see, P1 plus P4 plus P7 is equals to 1. So this is true. This is not true. Now it's saying that P2 plus P3 is equals to P5 plus 6. So yeah, we can say that because they both are equal to 1. So we can say that P2 plus P3 is equals to P5 plus say P6. The probability P2 plus P3 is equals to probability P5 and P6. So both the options are correct, right? So this is how we can study about state diagrams. Nice. Moving to the next question. Next question says that for the for the circuit shown, the clock frequency is F0 and the duty cycle is 25%. So duty cycle is what? The time. It is a time calculated when when basically the output is on. There are 2 possible options if we talk about digital. Either it can be on or it can be off. That is 1 or 0. So whenever it is 1 with respect to total time, that is known as duty cycle, right? So this it is saying that for the circuit shown, the clock frequency if not and the duty cycle is 25%. For the signal at the Q output of the flip-flop, So now what they are asking is, they are asking that what will be the frequency and what will be the duty cycle of the output, right? So this is a 2-bit binary counter. Counter means it will count the values. 2-bit means it will count up to 2 bits, right? So 2 bits start from, so if I am saying this is MSB, this is LSB, it will start from 0, 0, then it will count 1, then it will count 2, then it will count 3. That's the maximum counting of 2-bit. So this is a 2-bit binary counter. Now this LSB is given to both J and K. Both the J and K, LSB is given. Now let's just draw the clock first. Suppose this is my clock. So this is my clock. This is starting from t is equals to 0 and 1, 2, 3, 4, 5, 6 and 7 and so on. So this is my clock pulse. Now this LSB value is nothing but the value of J and K both. So LSB is what? It is changing from 0 to 1, 1 to 0, 0 to 1 and so on. So it is changing from 0 to, whenever the clock is given, to 1, 1 to 0 and so on. It is toggling. Similarly, K is also moving like this. Now output. Output Q. Now, in order to find out output Q, we should know the excitation table for JK flip-flop also. So here I am writing the excitation table for J and K flip-flop. J, K and output. So when JK are 0, 0, the output is previous state. Q, previous state. Right, when it is 0, 1, the output is 0. When it is 1, 0, the output is 1. And when both are 1, the output is next state. Toggle, sorry. Its output is toggle. The next state, the toggle. 1 and Q bar. So this is the excitation table for JK flip-flop. Right, now here, starting from this, we take another color. Starting from this, now we see for JK both equal to 1. What will happen? What will happen? If JK was equals to 0, it will leave into previous state. But when JK is equals to 1 and 1, J and K both are equal to 1, what will happen? The output will toggle, right? The output will toggle, and what will be the output? Sorry, when JK both are equal to, right, when we have to start from here, right? This is not t is equals to 0, this will be t is equals to 0 because starting was from 0 only. So this is t is equals to 0. Right. So this is t is equals to 0, 1, 2, 3, 4, 5, 6, 7, 8. Right. So previously, whenever the value of output is equals to 1, it will toggle the previous state. Now, the previous state was equals to 0. The previous state was equals to 0, so it will toggle and it will become 1. Now both are equal to 0. Both are equal to 0. That means it will remain in the previous state. So previous state was when it was equals to 1. Again, it is 1 and 1. Now when it will see 1 and 1, it will toggle the previous state. So previous state was equals to 1. It will toggle the previous state. When both are equal to 0, it will remain in same state. It will remain in the previous state. Again, what will happen? Both are 1 and 1. So it will toggle. It will toggle. Both are 0 and 0. It will remain in the same state. And again, 1 and 1 toggle. And moves like this. So previous state, whenever J and K hit value 1, so previous state was equals to 0. So 0 will be toggled. Got my point? So it is starting from this, right? It will see 1 and 1, both J and K are 1. It will toggle the previous state. So previous state was equals to 0. It will toggle it to 1, right? Here 0 and 0. There is no undo option, right? It's okay. Let me draw it again. Right. So now what's happening here? 0 and 0. For value 0 and 0, it will remain in the previous state. So previous state was 1, so it will remain in 1. Here again it will see 1 and 1, it will toggle itself. It was 1, it will become 0. Like this, the cycle will go on. Now if you see this output, see this output, this is the complete cycle of the output. This is the complete cycle of the output. Now it is completed in how much time? It is completed in starting from here. It will complete itself in 4 clock pulses. It will complete itself in 4th clock pulse is finished here. So it will complete itself in 4 clock pulses. So frequency will divide by 4. So frequency will divide by 4. And what about the duty cycle? So duty cycle is, it is on for 50% of the time. For this particular frequency F, it is on for 50% of the time. As I have told you, duty cycle is calculated when the in a time whenever the output is on with respect to the total time. So it is on for 50% of the time. So duty cycle is also 50%. So option A will be correct option. So frequency will become, so if this is F naught, it is going to take 4 clock pulses in order to give the final output. So it is F naught by 4, it will become F naught by 4 and duty cycle will become 50%. Okay. Moving on to the next question. Next question says that the propagation delay of exclusive OR, that is a XOR gate which is given here. Right. The propagation delay of exclusive OR, which is known as XOR gate, in the circuit is, so the delay is 3 nanosecond. The propagation delay of all the flip-flops are assumed to be 0. The clock frequency is provided in the circuit. So clock is 500 megahertz. 500 megahertz. Starting from the initial value of flip-flop, which will equal to 111, with D2 is equals to 1, the minimum number of triggering clock edges after which the flip-flop, so it's saying that it started from this, it have to end to this, and you have to find out the minimum number of clock pulses required in order to do that. Right. So let's just, now this is what, how much clock pulses? So T clock, if we calculate, so that will be 1 by 500 megahertz. So it will be 2 nanoseconds. So time clock time will be equal to 2 nanosecond. If I draw the clock here, so at t is equals to 0, at t is equals to 2 nanosecond, at t is equals to 4 nanosecond, at t is equals to 6, 8, 10, 12, and so on. I've just took a random clock. It is a positive triggered. So this is positive triggering here. Now, this is a circuit given. This is D2, D1 and D0. There are 3 flip-flops with D flip-flop, right? And here a XOR gate is connected to D2. So XOR gate value is, so XOR is giving output Y, which is equals to nothing but D2, and D2 is equals to what? D2 is equals to this XOR D0. So D2, or you can say not D2, Q2. So it is equals to, this is Q2 and Q0. Q2 XOR Q0. I hope you all know the truth table for XOR gate, right? So this is the output of the XOR. Output of the XOR is P2 and the input values of a XOR will be equal to Q2 and Q0. So initial values they have taken as 1, 1 and 1. So Q2 is equals to 1, Q1 is equals to 1, Q0 is equals to 1, and also the initial value of D2 is also given as 1. What kind of circuitry is this? This is shift register, right? Moving. Here input is given, the output is moved to next, the output is moved to next, serial in, serial out, shift registers are there. So what will happen? So at the first clock pulse, what will happen? And also the XOR will take 3 nanosecond. So let me mark 3 nanosecond timer also. XOR is having a delay of 3 nanoseconds. So somewhere here, so this is your 3 nanosecond. Again, three nanosecond is the delay for your XOR gate, right? This is your initial state, initial values, initial values. Now what will happen? Shift register is applied. So first clock pulse, it will become D2 value is given as 1. So 1 will be given here. It will shift itself. It will come to D2. It will come to this. It will come to this. But D2 value is provided by this XOR gate, but XOR gate will give output after 3 nanoseconds. So its value will be 1, 1 and D2 value will also be 1 at this 2 seconds. So it is also right. Now after this 2 seconds, what will happen? This will also again shift itself. This will again shift itself. So its value will be 1, 1 and 1. Now here after 3 nanoseconds, what will happen? This will become, XOR will give the output. So D2 here will become at 3 nanosecond. D2 will become 0. So when D2 will become 0, it will give output again. It will give 0 here. After 3 nanosecond, what will happen? D2 will become 0. So D2 will become 0. That means Q2 will become 0, 1 and 1. Now it will process here. It will shift itself. So it will, after 6 nanosecond, it will become 0. Now 0 is shifted to this also. So 0 will shift here. 1s are shifted like this. So this is how shift register will work. Now this will become 0. So it will be shifted like this, and these ones are shifted here. Right. So now 0 will remain same, and this 0 will shift here. This one will shift here. After 6 nanoseconds, again XOR gate will be activated. So XOR gate here, D2, because it is after 3 nanoseconds. So it will give the output. So 0, 1 output will be equal to what? 0, 1 output will be, for XOR gate, it will be 1. So 1 will be shifted here, and these zeros will be shifted here. So this is how the process will work. Final output, they are asking us to find out 1, 0, 0. So how many clock pulses it will take? 1, 2, 3, 4 and 5. So it will take 5 clock pulses. 1 clock pulse, 2 clock pulse, 3 clock pulse, 4 clock pulse, and after 5 clock pulses, the required output will be triggered. Now I will repeat it again. So what was there? I have drawn a clock. Initial values were given, but after 3 nanosecond, here after 3 nanosecond, after 3 nanosecond, the XOR gate will give the output, right? But it is a shift register, so D2 value will shift to Q2, and Q2 value will shift to Q1, Q1 value will shift to Q0, and Q0 will be given as output. So like it is shifting like this. If I draw it here, right? So just look here. So they were 1, 1 and 1, right? And it will shift on. When it is giving you 1, so 1 will shift here, this one will shift here, this one will shift here, and this one will go out. So 1 here shift after shifting 1 and 1, and this one is gone out. Now after 3 nanosecond, the output is processed as 0. So output 0 will come here, this one will shift here, this one will shift here. After this, 0 is only processed, so 0 will come here, this 0 will come here, and this one will come here. This one will go out. So this is how a shift register works. The same working we have done. So this is moved here, this is moved here. Similarly, D2 was 1, so 1 was there, this one will move here, this one will move here. After 3 nanosecond, D2 will become 0. So D2 will become 0. That means Q2 will become 0. Q1 will be 1 and this will be 1. It remains 0 because it has not processed the data again, because it has delay of 3 nanoseconds. So 0 will be there. D2 value was 0. So 0 will be there. This 0 will move to Q1 and Q1 value will move to Q0. After 6 nanosecond, what will happen? D2 value will again change, because this 0 and 1 XOR is equals to 1. So 1 will move here and 0 will move here, 0 will move here. So how many clock pulses it will take? It will take 5 clock pulses. Okay.